Welcome to IPM Works e-learning modules. My name is Ellie Dearlove from ADAS, and this video is part of Module 5, Invertebrate IPM. I will present Chapter 5.1, An Introduction to Invertebrate Pest Management. The main aim of this chapter is to introduce the overall concepts for invertebrate pest management. We will provide an introduction to the challenges of invertebrate pest management, specifically in relation to transitioning away from the reliance on chemical control options. We will introduce the concept of the art of doing nothing as a core philosophy for pest management. And finally, we will introduce the wide range of IPM tactics available for invertebrate pest management. Specific examples on IPM tactics are provided in the rest of the module. Insecticides, such as pyrethroids, are widely used across Europe. They offer a relatively inexpensive and highly effective option for rapidly reducing invertebrate populations. However, they are not specific to groups of pests, and so they can have large negative impacts on non-target invertebrates, including beneficial insects, as well as on the wider biodiversity in the surrounding landscape. Aside from the problems these chemicals pose to non-target species, many of the targeted pests have also developed resistance to active ingredients. In the UK, resistance to pyrethroids, for example, has been identified in more than 14 key pests, as shown in the timeline on the left. There are now established monitoring networks to track and identify the scale and potential impact of new resistant populations. Pyrethroid resistance, and other cases, have been driven by the high levels of use of insecticides, in terms of both the frequency of application within and between years, and the total area of crops pesticides are applied to. On the right, you can see the change in applications of insecticides in the UK since 1988, based on the FERA pesticide usage surveys, which do not include seed treatments. Insecticide use in arable crops doubled between 1988 and 1996, and continued on a slight upward trend since then. Pyrethroid use grew so rapidly that by 1996 it accounted for over 80% of insecticide treatments. Insecticides and other synthetic chemical pesticides are still widely applied to manage invertebrate pests. However, the availability of active substances is reducing. In the past, insecticides that were rendered ineffective due to resistance were replaced by the next generation of insecticides. But now, new insecticides are appearing much less often. It's increasingly difficult to find new actives that are as effective and which meet health and environmental standards. Newer substances coming onto the market are also more expensive than pyrethroids and other older products. The need to reduce pesticide inputs as part of a sustainable programme for improving human and environmental health, and the additional pressure of increasing pest resistance to synthetic pesticides drives us to rationalise our use of insecticides. Within a holistic IPM strategy, it's therefore critical that 1. IPM tactics are implemented that minimise the risk of pest infestations needing treatment, and 2. Where treatment is required, insecticide applications are well targeted to achieve control with the fewest number of applications possible. Insecticide resistance management is an important part of an IPM strategy, as it ensures that when insecticides are needed, they are available and they are effective. Insecticide resistance management is covered in further detail in Chapter 5.6 of this module. A pesticide-reliant approach to pest management can appear highly effective, and given the relative low cost of insecticides, it's often the default approach to invertebrate pest management. However, the wider impacts of excessive pesticide application are widely acknowledged, and the actual benefits to crop protection are often not as great as they may appear. Pesticide-reliant approaches are, at least, straightforward, so let's consider two scenarios. In our first scenario, a pest is targeted, an appropriate chemical is selected and applied, and the control appears to be achieved. Often, the effect is very visible. In outcome box A, fewer pests are now seen in the crop after treatment, and the crop is healthy, whereas in outcome box B, The application was not made, pests are observed in the crop, and the crop has suffered damage. This scenario is only true where the targeted pest was going to cause economic injury, which is not always the case. In our second scenario, a pest is targeted, but this time the pest was not a threat to the crop. However, if we look at the outcome in outcome box C, the result of applying the insecticide is the same as outcome A. Few of the pests are seen and the crop is healthy. This may therefore be interpreted as a success, but in fact the insecticide application was not necessary, and not applying anything would have had the same outcome, i.e. outcome box D. This presents a problem to farmers and their advisors because it isn't always clear which pests are likely to lead to economic damage until it's too late to act, and so insecticides are applied perhaps more readily than they should be. This is also where IPM plays a vital role, because where the farmer is confident that they have multiple tactics in place to prevent or mitigate for pest infestations, and they are using decision support systems and monitoring to track the potential risk posed by pests, they can then make the decision not to apply insecticides with more confidence. Pesticide-reliant approaches are more straightforward, but the long-term risks cannot be ignored. We illustrate here the relative complexity of an IPM approach. Given this, transition to a more advanced IPM strategies can be challenging and takes time. Many IPM tactics are available to choose from, and each may have trade-offs between impact on the targeted pest and impact on other pests, or yield, or other aspects of agronomy. The various IPM tactics highlighted here will be covered in later chapters in this module. Before going any further, we should define a few key terms. Crop injury is the effect of a pest feeding or other activities on the growth or appearance of crop plants. Crop damage is crop injury which leads to measurable loss of yield or a reduction in quality. It's important to note that crop injury does not always lead to crop damage. Economic damage is the extent of crop damage that justifies the cost of control. We can also note that crop damage does not always lead to economic damage. The economic injury level is the lowest pest population density that will cause economic damage. And the economic threshold is the pest population density at which control measures should be implemented to prevent pest populations reaching the economic injury level. The host plant resistance is the relative amount of heritable qualities possessed by the plant which influence the ultimate degree of damage done by invertebrate pests. And finally, host plant tolerance is the capacity for a crop to be injured without any discernible impact on yield. We will use these terms throughout the invertebrate IPM module. The easiest way to reduce insecticide use is to not use them at all, and it is possible to do this without risking crop productivity or profitability. An IPM strategy can comprise a number of components, for example, biological control, cultural control, resistant varieties, and transition can seem overwhelming. Arguably, the most important and easiest tactic to implement is to do nothing. The decision whether or not to do nothing can be among the most difficult that farmers and advisors face. Advisors' reputations are at stake, and often the short-term risk posed to crop performance are difficult to balance against the long-term risks of prolonged pesticide reliance. We need to be confident in the preventative tactics in place and the decision support systems used to inform on risks and pest thresholds used to assess the need for action. These are the key to deciding whether or not to implement a control strategy. We will look at preventative tactics, decision support systems and thresholds later in the module. However, it's worth acknowledging here that in pest thresholds we have a problem. Many thresholds were developed decades ago, and in the meantime, crop agronomy and varieties have changed. Many thresholds are not user-friendly. Insect activity is temperature dependent and counting small, very active pests can be a problem. Many thresholds have little scientific basis. We are more likely to use them if we understand how they were developed. We need to develop new, smarter thresholds in which we can have greater confidence. Collaboration between scientific disciplines is key to developing smarter thresholds. Entomologists and plant physiologists make the perfect team. Entomologists understand pest biology, pest assessment and control options, and physiologists understand how yield is determined and tolerance to plant injury. A further benefit of creating modern thresholds based on crop physiology and pest ecology is that the processes and concepts are clear to farmers and advisors using them. If the individual applies a threshold in the field and has a clear idea of the factors used to define the threshold, they are better able to adapt them to specific context. Crops have a built-in safety net. They can lose plants, leaf area, shoots or buds and still achieve potential yield. Crop tolerance is how much of which bits of the crop can be lost to pest injury without impact on yield, and understanding this is pivotal to developing smart thresholds. There is a difference between resistance and tolerance. With resistance, the pest is in some way prevented from causing injury to the plants. But with tolerance, the pest may injure the crop, but up to a point there is no associated damage. Susceptible plants incur damage related to pest injury. In order to decide when to do nothing, we need to know the size of the safety net, so how tolerant is the crop to pest damage, and how hungry is our pest. How many pests are needed to cause injury beyond what the crop can tolerate? Here's an example that shows how smarter thresholds can work. This logic will also apply to other cereal pests, particularly stem borers. Physiologists have also studied the parameters that affect yield and oilseed rape, so we can start to think about smarter thresholds in this crop. Wheat bulb fly lay their eggs in the soil. Larvae then emerge and they burrow into crops and begin feeding on shoots. This pest can be an issue in wheat, barley and rye. We know that cereal crops need 500 shoots per metre square at growth stage 31 to achieve optimal yield. We also know that adult wheat bulb fly on average lay around 125 eggs per metre squared, of which around 44% become larvae, that's 55 larvae per metre squared. And if each larvae kills on average around 4 shoots, amounting to around 220 shoots killed per metre square, if the crop has 720 shoots per metre square or more at growth stage 31, 220 of these could be lost to wheat bulb fly without any impact on the crop's ability to reach optimal yield. And so the farmer can relax. No need to do anything about this pest today. It's great to have so many options, as different IPM tactics can better suit different situations. For example, field, polytunnel, glasshouse, and different crops. The majority of IPM tactics do not provide total control in isolation, and some are codependent or mutually exclusive, but through strategic integration and combination, very good levels of crop protection can be achieved. More options means greater complexity, and with it, indecision of what controls to use and when. The IPM pyramid helps give some structure to the process of IPM tactic selection. IPM pyramids are the most successful and widely adopted means of bringing sense to the confusion and disorder from all of the IPM tactics growers have available. Put simply, an IPM pyramid is a hierarchical IPM decision support system, and it shows the range of tactics growers have available and places them at different levels of the pyramid, with the concept being that you should start at the bottom of the pyramid and work your way up, only if necessary, to access other tactics. If necessary is a key term here, meaning that you should only access higher levels of the pyramid if invertebrate damage to your crop is likely to exceed an economic injury level threshold. We can visualize this using the graph on the right-hand side. If we're monitoring pest populations, we can assign an economic threshold at which we should take action. This threshold is typically below the level where economic damage occurs, to allow time for any applied controls to reduce the pest population to a more sustainable level. The idea of IPM pyramids became widespread from the early 2000s because of how effective these pyramids are in illustrating the key principles of IPM. Typically, at the bottom of IPM pyramids are agronomic strategies and practices to avoid pest populations in the first place. These are crop rotation, resistant crop varieties, and in some cases, physical barriers. With these avoidance techniques in place, the next steps of the pyramid are typically about monitoring your crop for pests and damage and keeping an eye on pest forecasts. There are many pyramids out there, but the key principles of IPM pyramids is universal. Start by using the tactics at the bottom and approaches of the pyramid and work your way up as needed. Many authors have developed their own modifications to the classical IPM pyramids, emphasizing different aspects and moving elements around in the location in the hierarchy, as shown on the right here, with a pyramid that gives greater credence to the importance of IPM decision support ahead of the application of even cultural pest control measures. Monitoring your crop for pests and damage and keeping an eye on pest forecasts is key and a crucial stage in the pyramid, as it's through monitoring and forecasts that you can decide whether pest populations or damage have exceeded your threshold, triggering you to move to the next step in the pyramid. With this movement, we may include mechanical controls, biological controls, and only in desperate circumstances, chemical controls. Having just introduced the IPM pyramid and how we can make use of them, we do need to consider some complexities in their application. We know what tactics we have available and the kind of order that we should be using them in, but a further consideration is how these tactics interact and the impact of these interactions on the total level of pest management that we see. That is to say, the control that we get from multiple tools is not just the sum of their individual effects. Some IPM tactics can have positive effects on the efficacy of other tactics, while some tactics can cause other tactics to fail. To give an example, if we apply a biological insecticide, something like a plant oil, while this will invariably have an effect on the pest, it may also impact on any wild or introduced natural enemies of the pest in the crop. As the natural enemy populations are often slow to rebound in numbers following such treatments, this may mean that the pest population rebounds more quickly after biological insecticides have been applied, leading to an overall increase in pest number. The challenge then is anticipating these interactions between IPM tactics and trying to make use of beneficial interactions while mitigating negative ones. Unfortunately, one of the biggest challenges we face in IPM is that many of the interactions between IPM tactics are not well understood, and so all too often we cannot predict the outcome of different combinations of IPM tactics, and we have to use our best judgment. Nonetheless, being aware of these interactions is important, and we should always be thinking of interactions when we're thinking about our IPM systems. We also need to remember that IPM has a far wider reaching implication ecologically, politically and culturally, and in these scenarios the IPM pyramid is less applicable. The decisions that growers make in their IPM strategy have significant effects upon the environment and also their economic situation, and getting IPM wrong can have an impact on economic returns. Ultimately, IPM strategies need to be context-specific, built on the core principle of minimal intervention, and be sufficiently practical to cope with the fluctuating challenges of crop production between changing seasons. Some key points is that crops can tolerate some crop injury without any need for pest management action. Transition from pesticide reliance to advanced IPM is challenging but necessary. Invertebrate IPM strategies can be complicated, but they're built on a core concept of knowing when to do nothing. IPM pyramids can help build IPM strategies, guiding selection of hierarchical IPM tactics with the use of synthetic chemicals as a last resort. The rest of this module will introduce a range of concepts and approaches that can be applied to invertebrate pest management. Chapter 2 will be invertebrate pest injury and damage. Chapter 3, agronomic, mechanical and physical management options. Chapter 4 is biological control and biopesticides. Chapter 5, decision support systems and monitoring. And finally, Chapter 6, synthetic chemical pesticide resistance management. Please pause here if you would like to see the references or links to further resources.